Hello. In this video, I wanted to talk about an economic principle and also an application of how horizontal asymptotes arise. And we'll motivate this through a word problem. In this problem, we're going to talk about a vaccine manufacturer that wants to produce vaccines. So we'll say it costs the vaccine manufacturer $40 million to build a factory. That seems like a lot. I think that's around what they do cost. And then they're only producing vaccines for $4. So ultimately, they need to sell 10 million vaccines for it to be worth it to pay off the cost of the factory. But in this problem, we wanted to talk about what is the long run average total cost. So that is, what's the average cost of producing a vaccine over a long period of time? So this is asking, I guess, also what happens when you produce a lot of vaccines. How should the price change? For example, if we spent $40 million on a factory and then spent $4 to produce one vaccine, if we only produced one vaccine, we would need to charge 40 million and $4. And that's because that one vaccine you produce has to cover the entire cost of the factory. So being able to understand horizontal asymptotes and how producing a lot of these vaccines will help us understand how vaccine manufacturers might want to price their product. Because, for example, if we produced, let's say, 10 vaccines, so still a small number, then we need to recoup 40 million for the factory plus $4 times 10 for labor or production of the vaccine. But then we get to divide that into the cost of 10 vaccines. So the cost of the vaccine would go down to 4 million plus $4. So still ridiculously high, but way less than 40 million per vaccine. And so the cost of producing vaccines becomes very profitable in the long run. So when you're producing a ton of vaccines, it becomes really cheap. So for one more example, if we produce 10 million vaccines, then we have 40 million for the cost of the factory, plus 4 times 10 million for the cost of producing the vaccines. And we're going to split that into the number of vaccines that we produce. So we'll put the cost onto 10 million people. Now, all of these millions cancel out, and we're left with 4 plus 4, or $8 per vaccine. So that's a lot cheaper. All right, so let's get into the mathematics now. Let's build a function. This is college algebra. We love functions. So our function will be f of x. This function is going to represent the cost of vaccines, cost of a vaccine, where x is the number of vaccines produced or number of vaccines sold. And now we just need to recoup this cost. So we're just going to look at what it costs to produce X vaccines. So just like above, we'll write it out in all its glory this time, 40 million for the cost of building the factory, then plus 4x. Take a second and think about what that 4x should be. Maybe pause the video and think about what that 4x is representing. All right, so that 4x is representing the amount that it costs to produce X number of vaccines. It costs $4 to produce a vaccine. So if we produce X vaccines, we need to charge 4X for that. And then we'll divide by X. And this is so that we can take an average of our total cost. And so this is our function. And we can see that it's a rational function. We have a polynomial divided by a polynomial. And now we'll make one simplification of this function. We'll split up the fraction. So we'll write it as 40 million over X plus 4. When we split up the fraction, we'd have the 4X over X, and those two X's would cancel out. Okay, so now this is telling us how much we should charge for a vaccine, where X is the number of vaccines sold. And we're curious what will happen to this for very large X. All right, well, if we're starting just to check some values, and if we want to, we might also want to look at a graph and plot those values. All right, so let's put 10 million right here. Let's do 4, 8. And we already checked above that at 10 million, we would be charging $8. All right, but maybe this is a coronavirus vaccine, and you know you can sell at least 40 million of these vaccines. So if instead we had put 40 million, then all we have to do is plug 40 million into our function. Check F of 40 million equals, we had 40 million, we divide it by X, which is 40 million, and we add 4. And that just gives us back 5. The 40 million cancels with the 40 million to leave 1. So now we're down here at 5. So we already see that now we're getting much less dramatic changes, even though we're dramatically increasing how much vaccine we're producing. So when we went from producing 1 vaccine to 10 million vaccines, the price of the vaccine dropped from costing about $40 million down to costing only $8. But now we're producing 30 million more vaccines, and the price has only dropped $3 per vaccine. So it's not getting much lower. If we take this to the extreme, so we'll go all the way out here to 400 million vaccines, then we get F of 400 million, which equals 40 million over 400 million plus 4. That's going to boil down to 1/10 plus 4, so just a bit over 4. Now I'll draw on this dotted line. and we're just slightly above it. Now maybe we can see the behavior that's going on. We'll start to connect these lines. And that's going to start shooting way up on that side. All right, so this is the idea that 4 is our horizontal asymptote. That kind of makes sense. Our function's not going to drop below 4 because with each vaccine we produce, each vaccine itself still has to cost $4. The only thing we're accounting for in this function is how much should we raise the price of 4 to pay back that factory. And over time, when you produce a ton of vaccines, you can distribute that factory cost over so many vaccines. We saw in the 400 million example that we have 400 million people paying off $40 million. So they only have to pay a 10-cent premium. Whereas when it was only producing one vaccine, they would have had to pay the whole 40 million premium. And so that's how we can determine that 4 is our horizontal asymptote. We can see that if we scroll back up to our function, as x gets very large, this is going to be just about 0 for large x. When we divide a number by a very, very large number, it's about 0, and then we have to add 4 to it. So in the long run, our vaccine price is just about $4, so we don't even have to worry about the factory. And that is why economists have a phrase that fixed costs don't matter in the long run. And what it's capturing is saying that if you can build something that you know you're going to be able to sell a lot of. So for instance, Steve Jobs and Apple engineers had to put in a lot of time and energy developing the iPhone. They spent a ton of money on that. That was probably a huge fixed cost to develop the iPhone. But in the long run, they're able to sell so many that it actually becomes profitable to do it. So you should get a loan, pay those fixed costs up front, and then produce your item that a lot of people will want to buy. Of course, that breaks down, as we can see, if you don't have that many buyers. So this vaccine would be exorbitantly expensive if it was only there to treat 10 or 15 people. But anyway, so I hope this was a helpful introduction into understanding horizontal asymptotes. All right, see you later.